Hello everyone. In this session I'm going to teach you everything you need to know about factoring quadratic polynomials. I'm also going to teach you Vieta's formulas as a technique for factoring quadratic polynomials. Now, the topic of factoring quadratic polynomials is a part of a larger topic. How do we factor polynomials in general? To factor a polynomial means to take that polynomial and rewrite it as a product of two polynomials of smaller degree. Let me give you an example. Here's one polynomial, x squared minus 1, and I claim that x squared minus 1 is equal to the product of the polynomial x minus 1 times the polynomial x plus 1. So I've taken a polynomial of degree 2 and I have represented it as a product of two smaller polynomials. Smaller in the sense that the variable x here is raised at the first power. Okay, so here I'm having x to the first power, whereas here I'm having and here I'm also having x to the first power, whereas here I'm having x to the second power. Here's one famous example of a factorization, and here's another one. Now, are these factorizations correct? Let's very quickly check our factorization formulas. Now let's check the first factorization formula, x plus 1 times x minus 1. Now this is a famous formula and many of you will immediately recognize that that equals x squared minus 1, but nevertheless let's uncover the parentheses and check the factorization. We're getting x squared first, the first terms, then the outer terms minus x, then the inner terms plus x, and finally the last terms, so minus 1. So the two x's cancel and we're left with x squared minus 1. So indeed x squared minus 1 is equal to x plus 1 times x minus 1. Alright, so we verified the first of these two factorizations. Now let's verify the second one. Let's take the factorization of x cubed. So let's verify that x cubed plus 8 is indeed equal to x plus 2 times x squared minus 2x plus 4. So what I'm going to do is I'm going to take the right hand side. So I'm going to take x plus 2 times x squared minus 2x plus 4, and I'm going to uncover all the parentheses, and I'm going to check that I indeed get x cubed plus 8. So let me do that here. X plus 2 times x squared minus 2x plus 4 equals, alright, now x times x squared, that is x cubed, x times negative 2x, that is minus 2x squared, x times 4 is plus 4x, 2 times x squared is 2x squared, 2 times negative 2x is negative 4x, 2 times 4 is 8. Now before I proceed to simplify this large expression, let me make a quick error check. I'm going to count terms. So here I'm having two terms in this parenthesis, and in this parenthesis I'm having three terms. So two terms here. Here I'm having three terms. So in total I expect 2 times 3, 6 terms. I'm having 1, 2, 3, 4, 5, 6 terms. So the number of terms matches my expectation. So most likely I have not forgotten any term. Okay. So now let's see if there are any cancellations. Well, 2x squared cancels, 4x cancels, and I am left with x cubed plus 8. So indeed x cubed plus 8 is equal to x plus 2 times x squared minus 2x plus 4. Alright, so now we understand what is polynomial factorization, I want to make one very important note. Polynomial, for us to have a polynomial factorization, we need to break a polynomial into a product of polynomials of smaller degree. So fake factorization doesn't count. So what do I mean by fake factorization? Well, some devil's advocate may say, well, look, x cubed plus 8, I could factor that as 8 times x cubed over 8 plus 1, right? That's certainly representing x cubed plus 8 as a product of two expressions. Yes, that is correct, but this expression here, x cubed divided by 8 plus 1, has the same degree, namely the degree 3, as a starting polynomial. So that is not a factorization. So not valid factorization. Okay. Once again, what makes this into a non-valid factorization is that it is indeed it is a representation of a polynomial into a product of two other polynomials, but one of the polynomials has constant degree, is degree 0, and the other polynomial has the same degree as the original polynomial. That doesn't count. Okay. All right. Now, I'm going to teach you how to factor quadratics, but I can directly tell you how to factor an arbitrary quadratic. I mean, here's how to do it. Take an arbitrary quadratic, ax squared plus bx plus c. Then you can factor it in the following way. You can factor it as a times x minus x1 times x minus x2. What are these x1 and x2? So once again, I'm having an absolutely arbitrary quadratic, ax squared plus bx plus c. A, b, and c are just arbitrary constants, so I'm having an arbitrary quadratic, and I can immediately factor it as the number a times x minus x1 times x minus x2. Now, of course, the problem is, what are x1 and x2? Well, x1 and x2 are the roots that would be obtained if I were to interpret ax squared plus bx plus c as a quadratic equation by setting ax squared plus bx plus c equal to 0. So what I can do is I can take that quadratic here, ax squared plus bx plus c, and I could set it equal to 0. Once again, this is a quadratic which is not a part of an equation, whereas here I'm constructing an equation using this quadratic. But once again, what I've written here is a different object from what is written here. So here I'm having a polynomial, and here I'm having an equation. Okay, so I can from the polynomial I can construct an equation, and now that equation has two solutions. The two solutions are given by two numbers, x1 and x2, and these are the numbers that we need to use in the factorization of our quadratic ax squared plus bx plus c. So in order to factor ax squared plus bx plus c, I need to construct first polynomial equation, this polynomial equation, and then I need to solve it. And in the solution of that polynomial equation, I'm going to find numbers x1 and x2. These will be the two solutions of that polynomial equation, and I can plug them in this formula to get a factorization of my quadratic. Now, of course, how are these numbers x1 and x2 found? Well, we remember from our high school that the number x1 is obtained by taking the quadratic formula, and same with the number x2. So x1 is given, x1 and x2 are given by the formula minus b plus or minus radical of b squared minus 4ac over 2a. That is our familiar formula for solving a quadratic equation. In the preceding slide, I showed you how to factor an arbitrary quadratic polynomial using the formula for the solution of a quadratic equation. Before I show you an example, I want to teach you a shortcut method for factoring quadratics. This shortcut method is known under the name of Vieta's formulas. I'm going to suppose that there is a very nice factorization of my quadratic using integers alone. Now, if you remember in the theoretical slide, the factorization that were guaranteed by theory potentially involved square roots, radicals. However, I'm going to imagine that there is a factorization using integers alone. That's not guaranteed to always be the case, but if it is the case, I'm going to show you a shortcut method for factoring a quadratic. So, suppose that there is a factorization with integers. Now, since I'm using integers alone, I have to have the coefficient in front of x in one of the terms times the coefficient in front of x in the other term, so the product of the two leading coefficients, the leading coefficient here and the leading coefficient there, so the product of the two leading coefficients must be equal to the leading coefficient of the other side. So if I'm to have a factorization of 3x squared plus 8x minus 11 into product of two linear terms, the coefficient of those two terms must multiply to the number 3. Okay, but the number 3 cannot be written in too many ways as a product of two integers. In fact, the number 3 is prime, which means that the number 3 is only divisible by itself and the number 1. Actually, plus minus itself or plus minus 1. So there are only two ways in which you can write the number 3 into a product of two integers. Number 3 is either 3 times 1 or negative 3 times negative 1. So, if I were to rewrite 3x squared as the product of the two leading terms here, I'd have to have that the two leading terms in these two parentheses are either 3x plus something times x plus something, or I'd have to have that the leading terms are minus 3x plus something and minus x plus something. But see that I don't really need to consider that case because I could always factor out the negative sign, and if I were to do that, I would get the same thing as what I've written in here. So once again, I can assume that if there is a factorization with integers, then one of the leading terms will be 3x and the other leading term will be x. Alright. So now, if I can find integers p and q, which make this into an equality, I'll have factored my quadratic. So now I'm going to teach you how to guess the numbers p and q. Alright, suppose that we've already guessed numbers p and q, and suppose that these numbers are easy to guess. So they're integers, right? So suppose we've guessed p and q. So let's uncover the parentheses. 3x times x is 3x squared. 3x times q is, well, 3 times 3x cubed. P times x, well, that's p times x. And p times q, that's, well, p times q. Alright, so we uncovered all the parentheses. Now let's factor out x. So let me factor out x to get inside the parentheses 3q plus p. So our quadratic is now 3x squared plus x times 3q plus p times q. Now let's compare the two sides of our equality. On one side we have the quadratic 3x squared plus 8x minus 11, and on the other side we have, well, the same quadratic 3x squared plus x times 3q plus p times q. So the only way for this to be an actual equality is to have that 3q plus p be equal to the number 8, because the coefficients in front of x must coincide on the two sides. Similarly, p times q must be equal to negative 11. That's this equality. So these two pairs of equalities, 3q plus p equal to 8, and pq times in p times q equal to negative 11. Those two equalities are called Vieta's formulas. All right. So now, our desire to find p and q that are integers now forces immediate, very serious restrictions on the numbers p and q. Since we want the numbers p and q to be integers, we know that negative 11 must be represented as product of two integers, and now the number 11 is prime, so the only two ways to represent it as a product of two integers is to have that negative 11 be equal to negative 1 times 11, or negative 11 is 1 times negative 11. No other way to do it, right? So that means that the numbers p and q must be plus or minus 1 and plus or minus 11. In other words, there are only two options that we need to try for p and q. So with all of that information, can you guess the numbers p and q? Feel free to pause the video right now and try to guess p and q. I'm sure you guessed it correctly. Of course, p is equal to 11 and q is equal to negative 1. There were only two choices, right? We either had to try p equal to 11 or p equal to negative 1, and q equal to negative 1 or q equal to 11. Let's test that this choice is indeed correct. For this choice to be correct, we need to have that 8 is equal to 3q plus p. So is it true that 8 is equal to 3q plus p? Well, if q is negative 1, that means that 8 must be equal to 3 times negative 1 plus 11, which is negative 3 plus 11, which is indeed an equality. So the numbers p equal to 11 and the number q equal to negative 1 make this into an identity. Therefore, we can factor 3x squared plus 8x minus 11 into 3x plus 11 times x minus 1. Our factorization is complete. But I don't know if you remember the theory. In the theory, the theory that we just covered in the preceding slide guaranteed us that a quadratic polynomial ax squared plus bx plus c has a factorization of the form a times x minus x1 times x minus x2. You will notice that the factorization we got here, 3x plus 11 times x minus 1, is actually not of this form. So what's going on here? Well, the theory guaranteed us that the coefficient a in our factorization can be pulled outside of the parentheses. But notice that here the coefficient 3, the coefficient a, is inside one of the two parentheses, not outside. So is that a problem? Well, no, not really, because you can take the number 3 and you can factor it out of these parentheses. Of course, when you factor out the number 3, you need to pay the price of dividing 11 by 3. So by factoring out the 3, you get the form guaranteed by the theory. Well, not quite. To get the exact form guaranteed as by the theory, you need to have negative signs both here and here. Now here we already have a negative sign, which is good, but in front of the 11/3 we do not have we have a positive sign. Well, that a positive sign can easily be transformed into a negative sign, because plus something is always equal to minus that thing. So once again, I transform the plus into a minus, and now my factorization is of the form a times x minus x1, this is x1, times x minus x2, this here is x2. Alright, my factorization is complete. Now you'll notice that this trick called Vieta's formula, so the trick that I just showed you, it is somewhat involved. It requires you to factor numbers and guess divisors and to do quite a few computations. Now, indeed, in practice, this method is faster than the theory, but let me show you how to factor the quadratic 3x squared plus 8x minus 11 entirely following the theory without using the shortcut method that you just saw. So let us now pretend that we don't see this part. So let's pretend that we haven't done this. Okay, so I'm pretending that we haven't done it, and I'm going to do the factorization entirely using the quadratic formula. So if you remember, the number x1 and x2 can be found directly using the formula negative p plus or minus radical of b squared minus 4ac over 2a, the formula for solving the quadratic equation. Okay, so let's do that. The number a equals 3, so that is my a. That's my a, that's the number 3. Okay. Next, the number b is equal to 8, so we get negative 8 plus or minus radical of 8 squared minus 4 times, and finally the number c is equal to negative 11. So we get negative 8 plus or minus radical of 8 squared minus 4 times 3 times negative 11 divided by 2 times 3. Please do not forget to put the parentheses around the negative 11. Alright. Now, 4 times 3 times 11, that's equal to 132, right? So 4 times 3 times 11 equals 12 times 11, which equals, well, I guess it equals 100, and so it equals, well, 12 times 11, that equals 12 times 10 plus 1, which equals 120 plus 12, which equals 132. Of course, if you can do such computations in your head, I welcome you to do so. So 4 times 3 times 11 is 132, and minus with minus gives you a plus, and 8 squared is of course equal to 64, and 2 times 3 equals 6. Alright. Now 64 plus 132 is equal to, well, 190 plus 6, so 196. Now we have radical of 196. You recall that 14 squared is equal to 196, right? Because 14 times 14 equals, well, let's see, 4 times 4 is 6, carry 1, 4 times 1 plus 1 is 5, and then we write 14 here, we add the 2, and we get 196. So 14 times 14 is 196. By the way, for the purpose of using this quadratic formula, I highly recommend to you memorizing the squares of the numbers from 1 to 20. Okay, so 196 is exactly equal to 14 squared, so radical of 196 is 40. So we get negative 8 plus or minus 14 over 6. Well, that equals negative 8 plus 14 over 6, or negative 8 minus 14 over 6. I recommend when you have plus and minus to unfold it into such a bracket like this. Okay, so I highly recommend that style of writing things down. Now negative 8 plus 14 equals, well, 14 minus 8 is 6, so that's 6 over 6, which is 1. And negative 8 minus 14 over 6 equals negative 22 over 6, which is negative 11/3. And now we see that in our form we have x minus x1, right? So times x minus x2, so x2 is now equal to 1. That is my x2. So in the factorization here we had a times x minus x1 times x minus x2, so x2 is equal to 1. And x1, the smaller of the two, is equal to negative 11/3, which is, well, we guessed that using Vieta's formulas, but you can see that we can also guess it entirely using this quadratic formula. Now, I leave it up to you to decide for yourself which of the two methods is easier. In my personal experience, my personal opinion is that Vieta's formulas are slightly easier and faster to do whenever they work. In the preceding discussion, I showed you two methods for factoring quadratic polynomials. The first method, theoretical one, was using the formula for a solution of the quadratic equation. And the second method was using Vieta's formulas. Now that second method, I was calling it the shortcut method. That second method, I didn't quite give you a systematic exposition of it. So let me do that right now. So suppose that I have already factored a quadratic polynomial. So suppose that I have my quadratic polynomial ax squared plus bx plus c, and suppose that I have managed to factor it in the form a times x minus x1 times x minus 2. If you remember from our example, what we could do is we could uncover the parentheses on the left hand side. So we could take this expression that we see on the left, and we can distribute all the parentheses. So that's exactly what I'm going to do right now. So let's uncover the parentheses on the left hand side. A times x yields ax squared. Next, a times x times negative x2 is the second term. Next, the third term is a times negative x1 times x. That's the third term. And the final last term is a times negative x1 times negative x2. Now this expression can be transformed a little bit. We notice from the second and the third term that a repeats and x repeats, so we can factor a and we can factor x from the second and the third term. We can also factor out the negative sign, and finally we're left with negative a times x2 plus x1 times x. So the second and third term can be factored, as I just showed you. And in the last term, we notice that negative x1 times negative x2 can be transformed to x1 times x2. So minus times minus equals plus. So a times negative x1 times negative x2 can be transformed to a times x1 times x2. Okay, now let us compare the two sides. On the left hand side, we have a polynomial, and on the right hand side we have the same polynomial. So the only chance for the two polynomials to be equal is to have that their constant terms be equal, which means that a times x1 times x2 must be equal to c. Now we can divide both sides by a to get that x1 times x2 must be equal to c divided by a. Similarly, let's compare the linear terms. In the linear terms on the left hand side and in the linear terms on the right hand side, the coefficients on the left hand side is minus a times x2 plus x1, and on the right hand side the coefficient of the linear term is b. So the only way for these two polynomials to be equal is to have that the coefficient in front of x on both sides is equal. So we need to have that negative a times x1 plus x2 be equal to b. Now we can divide both sides of that equality by negative a to get that x1 plus x2 must be equal to negative b over a. So these two formulas, x1 times x2 equal to c over a, and x1 plus x2 equal to negative b over a, are the so-called Vieta's formulas. The Vieta's formulas are named after the French mathematician François Vieta. Franciscus Vieta was his Latinized name. And I'm going to call these formulas Vieta's formulas to avoid the risk of mispronouncing the French name. Okay, now let's use Vieta's formulas to quickly factor the quadratic x squared plus 5x plus 6. In order to factor that quadratic, we can use Vieta's formulas. So we need to guess the two roots, x1 and x2, which make this factorization work. So we need to guess the number x1 and the number x2, such that x1 times x2 is c over a. And we need to guess numbers x1 and x2, such that x1 plus x2 is minus b over a. Now let's compute what c over a is equal to. C here is equal to 6. That's my c. And a, well, here we're having 1 times x2, so a is equal to 1. So the product of the two roots, the product of x1 and x2, must be equal to 6. So x1 times x2 must be equal to 6. At the same time, the sum of the two roots, x1 plus x2, must be equal to negative b over a. Now, b equals 5, so we get negative 5, over a is again equal to 1, so we get negative 5. So, again, by the other Vieta formula, we get that x1 plus x2 must be equal to 5. So x1 times x2 must be equal to 6, and x1 plus x2 must be equal to 5. Now, the divisors of the number 6 are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. So, the pair x1, x2, the pair of numbers x1, x2, must either be 1 and 6, because 1 times 6 equals 6, or 2 and 3. So x1 is either plus or minus 1, and then x2 is plus or minus 6, or x1 is plus or minus 2, and then x2 is plus or minus 3. Of course, you could also have the other way around, right? So you could have that x1 is plus or minus 6, and x2 is plus or minus 1, but that just corresponds to swapping x1 and x2. So I'm going to assume that x1 is the smaller of the two numbers in absolute value. Alright. So now there are few options to try, right? So I could try x1 equal to 1, x2 equal to 6. Then x1 plus x2 equal to 7, which is not equal to 5. So that option does not work. Next, I could try x1 equal to negative 1 and x2 equal to negative 6. Recall the sum of the two roots was 5 and the product of the two roots was 6. So now x1 plus x2, under that circumstance, x1 plus x2 is equal to negative 1 minus 6, which is negative 7, which is again not equal to negative 5. Oops, my bad, negative 5, right? So the sum of the two roots is negative 5. So that option is a no-go either. Okay, so the next option is x1 equal to 2 and x2 equal to 3. Now x1 plus x2 is equal to 5, which is not equal to negative 5, so that option should be discarded as well. And the final option is that x2 be equal to negative 2 and x3 be equal to negative 3. With that option, x2 plus x3 becomes negative 2 plus negative 3, which is exactly equal to negative 5 as desired. So x2 must be equal to negative 2 and x3 must be equal to negative 3. So since x1 and x2 are negative 5, we see that x1 and x2 must be 2 and 3. Must be negative 2 and negative 3. Alright, let's factor another quadratic. Let's factor the quadratic x squared plus 3x plus 1. Again, our first guess is to try Vieta's formulas. So, the product of the two roots of that quadratic must be equal to 1. So, if I were to have an integer factorization of my quadratic, I'd need to have that the product of the two integers is 1. In other words, if I were to have an integer factorization of my quadratic, I'd have to have that one of the roots is equal to 1 and the other root is also equal to 1, right? Because 1 times 1 equals 1. Or I'd have to have that one of the roots is negative 1 and the other root is also negative 1. Once again, negative 1 times negative 1 equals 1. There are no other integer options. Of course, there are many pairs of numbers whose product is 1. There are infinitely many numbers whose product is 1, right? Just pick whatever you want for x1 and then 1 over that number times x1 would be equal to 1. X1 not equals. So there are infinitely many pairs of numbers whose product is 1, but only 2 of those happen to consist of integers, either 2 ones or 2 negative ones. So let's try them both. X minus 1 times x minus 1, well, that's actually a square, or x plus 1 times x plus 1, that's also a square. And we remember that x minus 1 squared, right, so this guy here would be x minus 1 squared. We remember that x minus 1 squared is x squared minus 2x plus 1, which is not equal to x squared plus 3x plus 1. Similarly, x plus 1 times x plus 1 is x plus 1 squared, which equals x squared plus 2x plus 1, and that's again not equal to x squared plus 3x plus 1. So both of these options don't work. What does that mean? Well, that simply means that there is no factorization of that quadratic with integers. So what we have demonstrated is that you cannot factor x squared plus 3x plus 1 with integers. No easy factorization. Whenever there is no easy factorization of our quadratic, we have to resort to the formula for a solution of a quadratic equation. So once again, if we can't quickly guess a factorization using integers, we should not use Vieta's formulas. We should instead fall back to the quadratic formula. Let's do that. Okay, so let's use our quadratic formula. A equals 1, right, so the coefficient A here equals 1. We're having here 1 times x squared. So A is equal to 1. B is equal to 3. B is equal to 3. That's the number 3. And C is equal to 1. C is equal to 1. Alright, so now let's compute. 3 squared is 9. 4 times 1 times 1 is 4. 9 minus 4 is 5. So we get minus 3 plus or minus radical of 5. That's it. We cannot simplify that expression any further. 5 is a prime number, so radical of 5 can't really be simplified. So that's it. We found our numbers x1 and x2. There they are. So this is my x1. And this here is my x2. So I took those numbers from here, x1 and x2. Here are my two solutions. Now, we got our factorization. I challenge you to take that expression that you see over here. So take that expression and uncover all of the parentheses. So just distribute everything out, FOIL the expression completely, uncover all the parentheses, and check that when you do that, the radicals are somehow magically going to cancel, and you'll be left with the expression x squared plus 3x plus 1. So once again, I challenge you to uncover here the parentheses and check that you get x squared plus 3x plus 1. I'll not do that here. I leave that exercise to you. Okay, so let's summarize our observations. Sometimes when we have a quadratic, we have to use the quadratic formula, and sometimes we have to use Vieta's formulas. When should we choose to use Vieta's formulas? We should always try Vieta's formulas first when we're trying to factor a quadratic. So in order to use Vieta's formulas, we should quickly check the divisors of the constant term. And if those divisors are few in number, we should quickly try all the possibilities for x1 and x2 based on those divisors. And if we're lucky, we'll be able to guess a quick factorization and save ourselves from doing a lot of work. That is option number 1. Option number 2, suppose that this term that you see here has a lot of divisors, or suppose that we can't get it to work, or suppose that we're just simply too tired of trying various possibilities for Vieta's formulas. If that is the case, we can always resort to the quadratic formula. So Vieta's formulas are always a quick shortcut for factoring quadratics, which we may choose to avoid. Okay, now as our final example, let's factor the quadratic x squared plus x plus 1. Now notice that this problem is formulated a little bit different. The problem reads factor the quadratic, and notice what is said here, using complex numbers if needed. So this problem somehow implies that a factorization of that quadratic will use complex numbers. Let's see if that's indeed the case. We're having x squared plus x plus 1. Once again, the product of the two roots is 1. The integer options would be that both x1 and x2 be 1s, or x1 be negative 1 and then x2 is forced to be negative 1 as well. So these are the only two options of integer factorization. Okay, so we either have the factorization x minus 1 times x minus 1, or the factorization x plus 1 times x plus 1. Both of these don't work. The first one is a perfect square, x squared minus 2x plus 1, and that's not x squared plus x plus 1. And the second one is x squared plus 2x plus 1, which is again not equal to x squared plus x plus 1. So this expression here is equal neither to this guy nor to that guy. Okay, so both of these factorizations don't work. When our Vieta's formulas don't work. So when our Vieta's formulas are not helpful, when the divisors of the coefficient here don't seem to produce to help us guess an actual factorization, then we should fall back to the quadratic formula. Well, let's do that. There's no easy factorization, so we must use the quadratic formula. Once again, the leading coefficient a is equal to 1, having 1 times x squared here. So the leading coefficient is equal to 1. The coefficient b is again equal to 1. Here we're having 1 times x, and that's the number b. And finally, the coefficient c is equal to 1 as well. So here's the coefficient c. Alright, so let's simplify our expression. We're getting negative 1 plus or minus radical of negative 3 divided by 2. And just remember, radical of negative 3 is equal to radical of negative 1 times 3, which equals radical of negative 1 times 3. And remember, radical of negative 1 was by definition equal to I. So that becomes 3 times, radical of 3, my bad. That becomes radical of 3 times I. My bad, I missed the radical there. Okay, so now that expression becomes radical of 3 times I, and we're done. We have our two roots, x1 and x2. Right, so our two roots x1 and x2 are minus 1 plus or minus radical of 3 times I divided by 2. And our factorization can now be completed. This is x1 here, x1, one of these two guys that when you select the plus, and this is x2 here. It's x2. Alright, we have now fully factored our quadratic x squared plus x plus 1. Notice that our factorization here uses complex numbers. Factorizations of polynomials are unique up to shuffling the multiplicand, so up to swapping those two polynomials, and up to multiplying by constants. So factorizations are unique up to shuffling multiplicands and multiplying by constants. I haven't demonstrated that fact, but it is a fact of algebra. So because of that, we are guaranteed that this polynomial here cannot be factored using integers, right? Because we already found one factorization and it used complex numbers. So we know that we cannot escape from complex numbers if we want to factor x squared plus x plus 1. So let's recap everything that we learned so far. When we want to factor a quadratic, there are two approaches. We could either use Vieta's formulas. Those Vieta's formulas are helpful when we can quickly factor the constant term of our quadratic, and the factors are not too many. So we could try to guess a factorization. And if we cannot guess the factorization, we should then resort to the quadratic formula. So case 1, Vieta's formulas work. Case 2, Vieta's formulas don't work, or we can't make them work, then use the quadratic formula. And in case 2, we had two subcases. The first subcase would be we get a factorization using the quadratic formula, in which both of the roots are real. And case 2, we get a factorization using the quadratic formula, in which both roots are not real. So these are the three possibilities for factoring a quadratic. Vieta's formulas work and we have an easy integer factorization. Option 1. Option 2, we have to resort to the quadratic formula, and in option 2, two sub-options, real roots or complex roots.